Think about how many times you interact with machine learning before you even finish your morning coffee. From unlocking your phone with just your face to that exact, perfectly timed song your streaming app recommends. It's everywhere. Welcome to This Explainer. Today, we're taking a seriously fascinating journey to demystify all these buzzwords. We constantly hear terms like AI, models, training, but what do they actually mean? Our goal today is to break these concepts down clearly and visually, and the best part, we're not going to look at a single line of code. We are building your understanding from the ground up. Let's get into it. Okay, let's dive into this by looking at how machine learning just fundamentally changes how we solve problems. Imagine, for a second, we want to predict the weather. The traditional programming approach means trying to create this insanely complex physics-based representation of the Earth's atmosphere. You're computing massive amounts of nearly impossible fluid dynamics equations. It's a headache. But look at the machine learning approach. Instead of hard-coding all of that physics, we just feed a system enormous amounts of historical weather data until it naturally learns the mathematical relationships between different weather patterns. It's a total game changer. It literally flips how we've done computing for the last 50 years, totally upside down.
Here's our roadmap for the explainer. We're going to start by moving beyond traditional programming, map out the 4 types of ML, zoom inside supervised learning, uncover how models actually learn, and finally, reveal the true power of your data.
All right, Section 1, Beyond Traditional Programming. Let's define the core of ML. We really need to establish exactly what sits at the core of this whole technology. You're going to hear the word model thrown around a lot, and it's super important to understand that a model is not a physical piece of computer hardware. As the definition points out, it's purely a mathematical relationship derived from data. Think of it kind of like a software brain. Through exposure to data, this software brain learns patterns so that it can eventually make really useful predictions or, even generate entirely new content. Moving right along to Section 2, the 4 types of ML. Let's map out the landscape. So how exactly does a model learn all this? Well, the first and definitely the most common type is supervised learning. So the crucial point is that in this approach, a human actually provides the system with data that already contains the known correct results. It's exactly like a student learning new material by studying old exams that have both the questions and the answers. Once that student studies enough of those old exams, boom, they're prepared to take a brand new one.
Now, what's really wild is how unsupervised learning flips that whole concept right on its head. Here, the computer doesn't know the answers beforehand. We just hand it a bunch of raw data, and its job is to naturally identify meaningful patterns or groupings, which we call clusters. So say you run an online store. An unsupervised model could look at your user behavior and naturally cluster your visitors into distinct groups, like your deal hunters over here and your Windows surfers over there, all without you ever defining those categories for it. It just figures it out. Then we have our third type, reinforcement learning. And this is a fascinating system built entirely on rewards and penalties. The model basically navigates an environment and figures out a policy that defines the absolute best strategy to maximize its rewards. This is the exact type of machine learning they use to train robots to perform physical tasks, like, walking around a completely new room, or how that software program AlphaGo mastered the wildly complex board game Go, which, by the way, was an absolute landmark moment in tech history.
And finally, the one everyone's talking about. Generative AI. This is a class of models specifically designed to create entirely unique content based on user input. Think of generative AI like a cover band learning to sound exactly like your favorite music group, or maybe an artist studying a very specific painting style. To pull this off, these models actually use an unsupervised approach initially, just mimicking the massive amounts of data they were trained on, so they can eventually produce totally new, original data. They aren't just copy-pasting bits and pieces, they are legitimately creating. And this brilliantly illustrates how we categorize these models in the real world, by their inputs and their outputs. It's pretty straightforward. If you give a model some text to, say, write an essay, that's text to text. Think Google's Bard. If you type in some text describing an alien octopus reading the morning newspaper, and it spits out a highly detailed picture of exactly that, well, that's text to image, like Imagine. You can even use text to video models like Phanaki to generate entire moving scenes. The combinations here are just incredibly versatile. All right, Section 3, Inside Supervised Learning. We're looking at regression and classification. Let's zoom back in on that very first type we discussed, supervised learning. I want to focus here because it solves 2 incredibly distinct kinds of real-world problems, regression and classification. Honestly, it all comes down to what exactly you are trying to predict. A regression model predicts a specific numeric value. So if you're trying to predict the exact price of a house or the exact number of minutes your rideshare is going to take to arrive, you use regression. On the flip side, classification models predict whether something belongs to a specific category, figuring out if that annoying email is spam or if a photo actually contains a cat. That requires classification. It's numbers versus categories. Okay, let's do a quick test. If you had a data set of flights and you wanted to predict the cost of an airplane ticket for an upcoming trip, which model would you need? Think about it for a second. Are we using regression or classification?
The answer? It's regression. Because the cost of an airplane ticket is a specific numeric value, say $450, you absolutely have to use a regression model to calculate it. A classification model? Well, that would only be able to tell you a broad category, like whether the ticket was going to be high cost or low cost. And let's be real, that doesn't really help with the actual dollar amount you need for your everyday budget, right?
Moving on to Section 4, how models actually learn. Let's talk about the training loop. So we know what these models are trying to predict, but how on earth does the software actually get smart enough to pull it off? Well, it all starts with the anatomy of a dataset. In supervised learning, your data is split into two things, features and labels. Features are basically your clues. In a weather dataset, your features would be things like the latitude, the temperature, the humidity. And the label? That's the spoiler. It's the final answer you want the model to eventually learn to predict, like the actual amount of rainfall. Whenever you have an example that contains both the features and the label, we call that a labeled example. Let's move to and see how this builds into the actual training loop itself. So the model takes in one of those labeled examples and it takes a guess. It makes a prediction. Then it compares its prediction to the actual true label. The difference between its guess and reality, we call that the loss. Based on that loss, the model goes back and tweaks its mathematical solution just a tiny bit to get a little closer next time. And it repeats this process over and over and over again for every single example in the dataset, gradually updating its understanding until those errors are as small as humanly possible. But here's the thing. We can't just cross our fingers and assume the training worked perfectly. Before releasing any model out into the wild, we have to evaluate it. We basically give the model a blind taste test. We take a totally different data set, but this time we hide all the labels from the model. We only feed it the features, ask it to make its predictions, and then we humans compare its answers to the hidden true values. That's how we see if it actually learned the underlying patterns or if it was just memorizing the test. Once the model passes that evaluation phase, we finally reach the ultimate goal, which is inference. Inference is simply using our fully trained, fully tested model to make predictions on completely new, unlabeled examples out in the real world. It's exactly like giving your smartphone's weather app today's current humidity and temperature so it can successfully predict tomorrow's rain. That's inference in action. And that brings us to Section 5, the power of data, specifically size and diversity. Listen, the math and the training loop we just talked about, that's really only half the equation. The dataset itself dictates everything else. A machine learning model is quite literally only as good as the examples we use to train it. So the ideal dataset has two absolutely non-negotiable characteristics: large size and high diversity. You need a massive number of examples, sure, but they also have to cover an incredibly wide range of scenarios. Think about it. If you have a ridiculously large dataset with, say, 100 years of weather data, but it only contains data from the month of July, well, using that to predict rainfall in January is going to produce some genuinely terrible results. To really see why both of these are absolute must-haves, just look at what happens when you compromise on either one. A huge dataset with low diversity, it completely misses the sheer variability of the real world. But a tiny dataset with high diversity is just as flawed. The models simply won't have enough examples to confidently lock onto any reliable patterns. So to generalize well on novel data, your dataset absolutely positively must be both massive and highly varied. There's no getting around it. Which leads us to a final kind of provocative thought for you to ponder. If these models are simply reflections of the data that we feed them, what unseen biases or missing pieces of information might be hiding inside the datasets powering the apps you use every single day? Every single time you interact with a digital system, you are generating the features and the labels for tomorrow's models. Just something to keep in mind the next time you hit accept. Thanks so much for joining me on this explainer today, and keep learning.